let me give some examples of quotient rings, meaning identify some quotient rings with rings that we have already seen. And all the verification will use the first isomorphism theorem. So here is the first isomorphism theorem again. Up here, let me remind you, and slightly differently. So if you have a surjective ring homomorphism, let's say, psi from R to S, let I be the kernel of this homomorphism. In any case, you have a, so then I is an ideal in R, and you have a quotient homomorphism from R to R mod I, taking an element to its coset. The statement is that the psi induces an isomorphism from R mod I to S. We called it eta. And this diagram, as they say, commutes, which means eta of a coset is psi of the original guy. Okay. So in particular, R mod I and S are isomorphic. In particular, if you have a surjective ring homomorphism, then the domain modulo the kernel is isomorphic to the image. Okay. The first one is no surprises. Ideals in Z are, you know, these guys, and Z for some n greater than or equal to 0. This is an easy exercise. One verifies that the quotient ring is same as, guessed it, Z mod n. I mean, we know this as groups. I'm saying this is true as rings as well. Nothing much here. 2 is already, I picked a rather non-trivial one. So recall, we had this ring S, which is, as I said, just R2, let's say, with usual addition, but a curious multiplication defined by AB times CD. A, B, C, D are real numbers here, is AC and then AD plus BC. When we introduced it, told you that you can think of this as set of all degree 1 Taylor series. So this is actually a commutative ring. The 0 is 0, 0, and the 1 of this ring is 1, 0. Okay? So to define a homomorphism alpha from the one variable polynomial ring with real coefficients to this ring S. So define this function alpha from polynomials to S by alpha of a polynomial is the polynomial evaluated at 0 and its derivative evaluated at 0. By derivative, I mean the calculus derivative. It's after all a polynomial, which is a function. You can differentiate it. Okay. You just have to know the rule that derivative of sum is sum of derivatives. Scalars come out, and the derivative of x to the n is n x to the n minus 1. Okay. So here's the first exercise. Verify that alpha is a surjective ring homomorphism from Rx to S. That's part A. And part B is check that the kernel of alpha is all polynomials which have 0 constant term and 0 coefficient on x, meaning all polynomials which are multiples of x squared. So what that tells you by first isomorphism theorem. So what's the setup? Here you have Rx to S, this map alpha, and the kernel of this alpha I'm claiming is all multiples of x squared. So here you have Rx mod the kernel, so these will be isomorphic. So by first isomorphism theorem, this S, this curious thing, is really just isomorphic to Rx mod x squared. So this a comma b corresponds to a plus bx. But notice that in this ring, the coset of that, if you will, that's the name of the ideal, the coset of a plus bx. But notice that in this ring, x squared is equal to 0, literally. So it's like taking R and adding an infinitesimal element x to it, whose square is equal to 0. Okay. How does this part B follow? Let's check part B just a little bit. Why is the... I'll leave the verification that this is a homomorphism to you, so you have to just to check that alpha preserves addition and multiplication. Addition is clear. Multiplication, you'll see that this curious multiplication law is exactly made so that this is a homomorphism, that the map is multiplicative. Okay. So let's just check that effect. I have this. And let's do it here. Sketch of B. Why is the kernel x squared? Well, if you have a polynomial that's a multiple of x squared, then f looks like, if f is in x squared, then f is x squared times some other polynomial. So it looks like that. So f of 0 is 0, and its derivative at 0 is also 0. So alpha of f is 0. Conversely, so it's in the kernel of alpha. If f of 0 and f prime of 0 equals 0, then write f equals a0 plus a1x plus a2x squared plus dot dot dot, and writing fx equals that, we find that a0 is just f of 0, so that has to be 0, and a1 is just the derivative at 0, so that also has to be 0. So again, fx starts from a2 x squared plus a3 x cubed plus blah blah blah, so it's a multiple of x squared. So that's essentially why part B is true.